Okay, so we can start. So we're happy to have for the last talk of the day, Tomoki Nosaka will tell us about new recursion relation for M2-brane matrix models. Please.
Thank you for the introduction. Let me thank you guys for inviting me to this nice conference on nice place. It's very, I'm very happy to visit Beam site first time for me and give a talk here. So, as already introduced, my name is Tomoki Nosaka. Now I'm in Shimis in Shanghai, and today I'm going to talk about some my bit old result on the partial function of M2-branes. So in this talk, I'm going to consider the theory of M2-branes, which are 3D supersymmetric case theory, which have several properties. One property is that it must have the 8-dimensional moduli space because we are considering the M2-branes in 11-dimensional space time. So 11 minus 2 plus 1 is 8. And if we have n M2-branes, which means the rank of gauge group is n, the moduli space contains this R8n divided by the symmetry group. And another important property is that the degree of freedom is scaling in the large limit as n to 3 half. And more concretely, what I mean is if I calculate the S3 partial function of the theory of M2-branes and take the log and put minus, it's called free energy, it's scaled n to 3 half in the large limit. And just in case someone don't know about this, I wrote some very brief summary of how we get this n to 3 half. So let's suppose there is an ADS-FT correspondence, then M2-brane is equal to the ADS4 plus some Y7 spacetime. This Y7 depends on which kind of M2-brane theory you're considering, but anyway, let's assume this spacetime, or this matrix is governed by a single length scale. Let me call it LADS. And the relation between LADS and the N can be estimated by considering the behavior of the tree form, which is the generalization of the electromagnetic field. But in this case, it's like electromagnetic field living in the transverse direction, 11 minus 3. And just generalizing it's 1 over R behavior of the electromagnetic potential, we find the 3 form must behave like this. And from this, we conclude that the length scale must be n to 1.6. And the ADS-FT tells us that the partial function of M2-branes, the partial function with supergravity. And just by dimension counting, we get this, and if I plug this length scale, we get n to 3 halves. And one typical example of the theory of M2-branes is the efficient theory found by Horony, Bergman, Joffre, Matsuna, and I think it's slightly before, also by Hosomichi, Lee Park. And this theory is given by this quiver diagram. And what the quiver diagram means is that each node correspond to each node with UNK correspond to the n equal to Chern-Simons vector multiplet, and each edge correspond to the hypermultiplet in certain representation, which you can read from the quiver diagram. And as it already appeared in Leo's talk, we can apply the Suji localization. So usually it's difficult to calculate the partial function in quantum field theory, so it's very difficult to verify check this n to 3 half. But the good thing is that due to supersymmetry, we can do it. And as already explained in Leo's talk, we can deform the action in the calculation of this path integral without changing the value of the partial function. And if I take this t infinity, the partial function, the path integral localized to the certain very special configuration, which is annihilated by the Suji transformation. And summand is just given by the original action value at the saddle, localization loci times the one loop effect. And we can apply this to the various theory. And if I apply this to the efficient theory, we obtain this. And the relation between this general formula and this matrix model is that in efficient case, we have this 2 gauge node, and the localization loci is characterized by 2n real numbers, which are the wave of the scalar component of the Chern-Simons vector multiplet. So we have 2n real values, so instead of summation, we have the integration. But anyway, it's much better than path integral. And this original action term is this. This comes from the Chern-Simons, super Chern-Simons action, or only super Chern-Simons action privilege. And the remaining products, bunch of products are the one determinant. And yeah, as this color shows, the numerator comes from the vector multiplet, and the denominator comes from the hypermultiplet. And maybe we can evaluate the large N behavior of this patch function by the so-called large N saddle point approximation. What it means that I put all the integrand into the exponents and then do this other approximation. So just approximate this integration itself by the integrand at the stationary point. So in user saddle point approximation, you expect there is some parameter which control the accuracy of the saddle approximation, but in the current case there are not such continuous parameter. But still, the exponent typically scales in n. So n, when n is large, this n plays role of the power parameter which justifies saddle approximation. Yeah. Yeah, actually, we don't care much. This part doesn't diverge, so it's Fresnel integration. So if some conversion value is rapid oscillation to infinity conversion. Product of change comes from the one-loop determinant of the vector multiplet. That comes from the one-loop determinant of the hypermultiplet. Now, hypermultiplet are in the by fundamental representation. And what I'm doing is the one-loop determinant of the Suzuki transformation square operator, and this contains the in user supersymmetry in flat space, you have the derivative, Suzuki squared derivative. But we are considering gauge theory, so derivative is covariant derivative. And since the vector multiplet appear in the together with the various other components, we can easily guess that the delta square, so the square also contains the gauge transformation generated by the scalar component vector multiplet, and that's part to give this x dependence. So maybe we can evaluate the patch function in by the saddle point approximation, and this is ansatz both in this paper, and yeah, then we find something nice happens. First thing is that if I plug this ansatz to the interaction part comes from this part. Then the naive n scaling is, since we have the double sum and the log change, log and exponential cancel, so we have n squared times the square root of n. So naive n dependence is n to 5 halves, but actually that leading part cancels because of this minus minus plus. And we have the subleading part is n to 3 halves. This is the first nice thing. And the second nice thing is that if I plug this ansatz to the potential part, yeah, let me call this chance action part, that's the potential part. Then again, the naive leading part is n times the square of the square root of n, so n square, but again, the naive part cancels because we have x square minus y square. And the subleading part is n to 3 halves. And since we want to find the saddle solution, well, what we have to do is to find a certain configuration which balance the contribution from potential term and contribution from interaction term. But since both of them, so yeah, in order to have the balance, the necessary condition is that they must scale in the same power n, and that thing is satisfied. And actually, no, k is an infinite number. No, not necessarily one. Yeah, I think people first took the limit, but in this talk I consider only the M3 limit. K is fixed and then it's large. And yeah, this solution, this answers indeed turned out to solve the Sodal equation. So we can even determine this. Sorry, I forget to explain, but AI and BI, when you send n to be very large, what I assume is there are some smooth configuration in depending on this variable. And we can even determine the concrete expression for this A and B1, B2. Sorry, I forget it, but yeah, it's nice. And it gives the display energy. And actually, not only for eVision, but also for any quiver. This quiver means on each node we have some chance time encoded vector multiplet, and each bond is the hypermultiplet. We can just apply. So we can just interpret this as some quiver Suzuchan. No, here I'm not assuming balancing, but if we want to get n to 3 half, it must be balanced. Yeah, that's what I'm going to say. Yeah, but if you just want to apply the localization formula, you can do it to any quiver. So, and if you apply it, as I did in the previous slide, each gauge node, so each vector multiplet gives this one determinant, and each hypermultiplet gives the one determinant. So I'm taking the product over the possible bonds. Yeah, I try to draw the as generic quiver as possible. And by generic, what it means that the number of bonds is arbitrary. So even the number of bonds connecting the same nodes can be not necessarily 0 or 1, but it can be 2 or 3 or any. And from each node, we have this chance function. And we can again try to evaluate this partial function in the large sort of approximation. And let's assume the same answers as the previous slide, and let's suppose the same lucky thing happens also now. Then what I mean is the leading behavior of the contribution from this one of the determinant, which I call the potential term in the previous slide. So interaction term in the previous slide cancels. And I don't know whether this is common language or not, but at least in the paper I read, this condition is called the long range force cancellation. So yeah, the reason is that so almost all contribution cancels, and only those where xi minus xj or xi minus xi a minus xj b or xi a minus xj b are small remain. So the long range part cancels, on the short range part remains. And actually, this condition automatically require the quiver to be ADE. No? Yeah, I think so maybe I'm memorized it. Yeah, so sorry if I'm wrong, but at least for the AD case, this condition is satisfied. But what I mean here is this condition must be satisfied for all gauge nodes, and that is satisfied by this type D, type E6, E7. So yeah, fine. And another condition that the leading contribution from potential cancels means this. Yeah, this is just one condition, not condition for each node. So yeah, this can be just easily satisfied just by tuning. And actually, there's a slight generalization, which is you can add any number of fundamental hypermultiplets to each gauge node. And because this doesn't change this counting of the leading behavior. So you can do any number of hypermultiplets, fundamental hypermultiplets, and still the large n, large n for linear scale n. And you can also add the adjoint hypermultiplet to each gauge node. And actually, this adjoint hypermultiplet change the argument of this long range force cancellation. So actually, if we introduce adjoint hypermultiplet, more general quiver are also allowed. So yeah, actually, I said too many technical things, but what I wanted to say in this slide is that there are really many theory of M2. So natural question is so far I considered many theories which show the N2-3 have scaling. So what is the universal structure? No, not in the leading, but in the also sub-leading part of the Lagian expansion. This is natural question, I think. And actually, to study sub-leading part is not easy, especially if we are interested in the all order collection. But in, for example, in the epidemic theory, it was done by Marcos and Pavel Petrov by so-called Fermi-gas formalism. And this result itself was obtained in different way, but I want to stress Fermi-gas formalism because it's applicable to many other examples. Anyway, by using Fermi-gas formalism, we can rather easily get to this final answer. The S3 patch function behave like the Airy function up to the non-particle corrections, and all the one-over-n correction is just given by the expansion coefficient of the Airy function, which looks like this. And actually, just in the same paper, Marcos also show that for any circular quiver, we can just do the same calculation. And once we have such Fermi-gas formalism, it's automatically arrives. So yeah, I think it's a natural question. And actually, yeah, I also thought that it's a natural question. So time to ask whether we can construct Fermi-gas formalism for also the other quivers or not. And yeah, actually, I and my supervisor and the different group succeeded in also the affine data quiver. And actually, so far, I was assuming that the rank variables are just precisely the value which is required by this long range force cancellation. But actually, we can add some order 1 fluctuation to each rank. It doesn't have violate the long range force cancellation argument at all. So yeah, but actually to construct the Fermi-gas formalism for such a rank deformed setup, even in circular quiver is not so obvious. But thanks to many efforts, actually in many, not all, but in many examples, rank deformation, rank deformed patch function is also written in the Fermi-gas form. But still, there are many setups where we still don't know Fermi-gas formalism, and yeah, I think it's likely that there are it's impossible to construct Fermi-gas formalism. For example, very easy example is some continuous deformation of the three-step patch function of, for example, the efficient theory. Continuous deformation, for example, by squashing or by introducing mass deformations. If I do the generic such deformation, the localization formula. So in the previous slide, I said that the one determinant of hypermultiplicity is just 1 over cos, but for generic deformation, it's much more messy function called double sign function. And then I don't know how to do it, how to do different formalism. But still, of course, there is some very special choice of parameters. Yeah, B equal 1 is also special choice of parameter, but for example, B equal skeleton 3 without any mass deformation is special parameter. And there are various very special choice of parameters for which we can do the Fermi-gas formalism. And yeah, interestingly, even for the case where the choice of special, but still we cannot construct Fermi-gas formalism, we can still calculate patch function, the exact value or just numerical value for n equal 1, 2, 3. Yeah, 3. Yeah, to increase n is difficult, but yeah. And so I'm considering various set theory of M2-branes. circular equivalent branes, and if someone found the rewriting of the patch function into Premiga Somalia. So I'm going to explain it in shortly. Yeah. So the patch function is originally given by this matrix model, but there is some nice rewriting called Premiga Somalia, and nice rewriting, reorganization of this integration. And yeah, once we have the expression in the Fermi-Gas formalism, we find the order of the one-by-one expansion is given by the ID function. Yeah, that's what this column means. And the interesting is that in this continuous deformation case, sometimes we can do the Fermi-Gas formalism, and in that case, it is obvious. But even there are some cases where we cannot do the Fermi-Gas formalism. But still, if I look at the exact values and then we find it's fit very well with the area function. So yeah, of course there are no proof, but yeah, I want to believe that the area function is maybe universal structure for the Laplacian expansion of the theory. And actually, some people in gravity side also study so the one-by-one correction should be related to the quantum correction in gravity side. So some people try to study the quantum correction in gravity side. And actually, the first two terms was also reproduced from the gravity side. Quite general setups. I think this log part was already mentioned in the last talk. But actually, log part was reproduced by quite at the early stage by these people. And rather recently, I think 2020, the group of Bob Webb and some people study the higher derivative correction and start to say about this into one. Anyway, these two parts are obtained for quite general setup in the gravity side. And in the gravity side doesn't care whether we have some nice matrix modeling case theory side so that it's allows Fermi-Gas or not. So I think this is another motivation to believe the area must be somehow universal structure. So what I wish to do is to find a way to show that the area one of the expansion is given by the area function for this still mysterious setups like this and of course one approach is just try even harder to find the way to rewrite patch function into Fermi-Gas formalism. Actually, I think in the beginning, people thought it's impossible to do the Fermi-Gas for non-circular case. But then, yeah, we find yes, I and this group of Drucker find the Fermi-Gas formalism for theta quiver. And then I think just after that, people also hope that maybe they can do the Fermi-Gas formalism for E-type quiver. And I think some people tried, but I'm not sure whether they are successful. So this is one approach. But another approach is maybe it's impossible to construct Fermi-Gas formalism, but maybe there's another way to study the follow the one-by-one expansion. And yeah, this talk is in this talk I'm going to tell you that we find some new recursion relation of the patch function with respect to n, and it might provide some new method to but yeah, there are two comments. One comment is that actually this method is not completely independent of the Fermi-Gas formalism. Actually, this method was discovered, highly motivated by the Fermi-Gas formalism. And another very disappointing comment is that so far I found on the recursion relation only for the M2 models where we already know the Fermi-Gas formalism. So we already know the answer. But yeah, I just hope maybe I can extend my analysis to generic case. So this is plan of my talk. So first I'm going to review the framing of formalism for efficient theory and how we can get the Gaussian expansion. Yeah, actually, we can get not only the order 1 over part of the expansion, but we also get the no part of the expansion. I'm going to comment both of them. And then I move on to the finite n property of the patch function. First, I comment on the binding equation satisfied by the finite n patch functions. And actually, this is the key ingredient to obtain the recursion relation. So then I'm going to talk about the recursion relation. So before talking about the framing axiomism, let me first say that in this talk, I consider only the circular case. And the nice thing of circular case is that it have a very clear type 2-brane construction, which consists of the D3-brane left on the S1 direction and the NS5-brane, D5-brane, or 1, K5-brane. 1, K5-brane means the bound state of NS5 and the K5-brane. And each branes are extended in this direction. And yeah, this is the example of the type 2-brane construction for circular fiber gauge theory. And these various colored lines are the open string, which gives the multiplet of the 3D theory living on the 0 and 2 directions. This red string gives the red strings stretched on the D3 branes separate. Stretching between 2, 1, K5 brane gives the Chern-Simon vector multiplet, and Chern-Simon level is given by the difference of the D5 charge, D5 charge. And this blue string stretches between 2 stack of the 3 branes separated by 1, K5 brane gives the fundamental hypermultiplet. And this green line stretches between D3 and the D5 brane gives the fundamental hypermultiplet. If we have many D5 branes, many fundamental hypermultiplet. And in this particular example, the quiver diagram. And once we have the quiver diagram, we can do the localization. And in this particular example, this is the localization. And if you compare this and this, you notice that there's a direct dictionary to write down, maybe without thinking of the quiver diagram, direct dictionary to write down the matrix model from this brane setup. Namely, if you have each segment, this brane, you assign the integration variables and you put this way, this integral. And for each 1, K5 brane, separating this brane assigned by x and this brane assigned by y, we insert this factor. And if we have D5 brane, we insert this factor. Sorry, I didn't explain in the introduction, but this is the one to determine the fundamental hypermultiplet. And yeah, then let me explain the framing axiomism. So for concreteness, let's consider the ABJ theory. ABJ theory means ABGM theory with in general non-equal ranks. And the brane setup is this. And this is the matrix model. And actually, the overall phase factor is in this talk just a convention. And the final answer is that we can rewrite this patch function into the patch function n-dimensional integration of some determinant of the matrix element of certain one-dimensional quantum mechanical operator, where the Planck constant is proportional to k. And this formula is obtained by applying the so-called Cauchy determinant formula. So this is a generalization of Cauchy determinant formula called Cauchy Fontermont determinant formula. Anyway, use this to rewrite the combination of Shinch Cauchy into the determinant. So we can rewrite the integrand into the product of 2 determinants. And then further notice that the matrix of the determinant, sorry, you have to insert substitute exponential x into this formula. So the matrix element of the determinant is 1 over Cauchy. And that 1 over Cauchy can be further written as the matrix element of the quantum mechanical operator, which is P operator in this case. So we have some determinant of the two determinants of some matrix element of quantum mechanical operator in the integrand. And then we use something called Andreev identity to combine the 2 determinants, and then we obtain this So sorry. What I said is for the case of m equal to 0. Yeah, in m equals 0, the application of undefined identity is limited. In m equal to non-zero case, the calculation is a bit tricky, but let me skip that calculation. And this is finite. Sorry, this is finite results for m equals 0, and this is finite result for m equals non-zero. And for in case of m equals 0, we can further do this symmetry transformation to rewrite this to this in much simpler form. Okay, anyway, let me comment one thing that in this calculation, we again notice that there is a direct dictionary to obtain the Fermi-Gas density matrix from the type 2-brane setup, at least when the relative rank m is 0. What it means that for each 1, k s5 branes, then we obtain this operator. And if we have, sorry, I didn't consider a case where we have the d5 brane, but when we have d5 branes, we have just one over Cauchy integrand, and it's just become the x operator. So for any circular quiver, we without relative rank. So when all the ranks are uniform, the number of these brane segments are same, we can immediately obtain the density matrix of the Fermi-Gas somewhat by applying this rule to each finance. So sorry, there is a type. If we have LD5 brane, this must be 1 over 2 cos x half to L. And once we have the Fermi-Gas somewhat, we can get the order 1 over expansion rather easily, as I said in introduction. So to study the Radian expansion, it's useful to consider not patch function directly itself, but consider the ground patch function first and define the ground potential. Sorry, modified ground potential J mu, which is defined by through the ground patch function. This is the ground patch function through this way. And by the way, this ground patch function is in the current setup given by the Fredholm determinant of this form. And so what we are going to do is to study the modified ground potential J mu, and once we know it, we can go back to the patch function by this inverse transformation. And this inverse transformation formula also suggests to us that the large n expansion of the patch function corresponds to the large mu expansion of the modified ground potential. So and we can study the large mu behavior of the modified ground potential in this way. So first take the derivative of J in mu. And let's ignore the subtle difference between the modified ground potential and just log of the ground patch function. Actually, if we are doing analysis in the small k expansion, there are no such difference. Anyway, then the mu derivative of J is mu derivative of log of the ground canonical patch function. And it's the what we learned is statistical mechanics. This is the expectation value of the particular number for given the chemical potential. If we identify the density matrix with the Hamiltonian in this way. And when mu is large, since we are considering ferromagnetic system, the particular number is, so if we have n particle just fill the ground state first and excess first, then from lower state to higher state. So it fill up to something called Fermi surface, where energy is equal to mu. And in the classical limit, this particular number below the Fermi surface is just given by the phase space volume. So this gives the mu derivative modified ground potential. And actually, this space volume can be evaluated very easily in the large limit because now, for example, for ABGM, this is density matrix, and this is Hamiltonian. Hamiltonian is log of this, so minus log of this. But when mu is large, x at the generic point on the Fermi surface, both x and p must be large. So log cost can be approximated just by absolute value of x or absolute value of p. So this is the result of the approximation. And then the Fermi surface is just diamond. And the volume is c mu square. We see some constant proportional to 1 over k. Sorry, volume is in this case h mu square. And h by dividing volume is c mu square, which is something proportional to 1 over k. And yeah, well, once we get to the immediate derivative of j, we can integrate it to get j. And this is the result. Actually, we found some cubic polynomial plus some non-particle correction in here. Sorry, I didn't explain how to get b and a, but you can obtain them just by doing the semi-classical small k expansion carefully. I'm not going to explain it in this talk. And then once we get to this, we just insert this to the inversion formula. Then, yeah, this is precisely the integration expression of the area function.
So this is only from something. So if you were to compute something after this analysis, like that, it's a function or this is only for function.
Yeah, in the Fermi-Gas case, yeah, I think the simple way is just claim through this integration formula as area, but as I briefly mentioned in the introduction, originally area was not obtained by the Fermi-Gas, but obtained by doing the two-state expansion. And sorry if I'm wrong, but they really write down the recursion relation for the expansion coefficient to the expansion, and then they conclude if you sum it, you get the area function. Yeah, actually, I have no concrete idea how to prove the area behavior with that Fermi-Gas. Yeah, so this is the analysis for the ABGEM, but for any general circular fiber, as I said, we can construct the density matrix systematically by applying this general rule. And of course, the density matrix looks slightly complicated, but anyway, Fermi surface are again some polygon. So the volume area, so volume means the Fermi surface is some mu square. So we can do complete same analysis. The only difference is just the C, B, A are some model dependent constants. And we can also study the one by non-particle effect. And let me first say what it means in what is physical meaning. Unfortunately, I don't know physical meaning in case theory side, but in gravity side, the meaning is that so far I say that the theory of M2-brane theory is 4 cross 1 by 7, but let's consider some another closed Euclidean M2-brane. So this is different from the Stack-Brane M2-branes. So some another closed M2-brane propagating the bulk and wrapped on some 3 cycling the Y7. And yeah, from ADS4 viewpoint, this looks like instanton, so this is called M2 instanton. So we can consider expanding the element-dimensional gravitational path integral by the contribution from just empty ADS4 cross Y7, and then the slightly modified spacetime where we have ADS4 cross Y7 with such one M2 instanton, two M2 instanton, and so on. And this SM2 inst is the weight of the M2 instanton action, and V, which is proportional to the volume of this wrapped three-dimensional volume. And since we have just one length scale, it's RADS cubed. And in the introduction, I just say ADS is proportional to n to 1 over 6, but if we also take into account k dependence, LADS is k to 1 over 6 times n to 1 over 6. So LADS cubed is this up to some constant. And if you take the log of this element of the spectroscopy Pasch function, the leading term is just contribution from this, and the subleading part is exponential to minus. Exponential to minus M2 instanton, and that means the non-particle correction to the free energy is this. And again, in order to study this non-particle effect, it's also useful to look at the ground potential rather than Pasch function. So yeah, if you remember this impulse transformation, actually, if we plug this to here, of course, that's the integration expression vary, but we can further say that we can get once we plug this to here, we can get the N2-3 behavior by doing Sadler approximation for this mu integration. And that tells us that roughly speaking, mu is related to square root of k. So if you have the non-positive effect which looks like this in the first function side, well, it means that in the ground potential side, we have such large mu non-positive effect with omega some number. And by the k dependence, we can classify such M2 instanton in two types. One type is the M2 instanton where the three-dimensional volume doesn't contain the zk over the cycle. And in this case, the exponent is just in the ground potential exponent is just mu, some constant times mu. And this effect can be studied by the semi-classical small k expansion analysis by this way. So what I did here is so ground first function is the Fredholm determinant, and J is log of Fredholm determinant. So I first expand the log determinant part, and we obtain this. And then we can rewrite this to this way. This can be done because the gamma function, this part have the poles at positive integers, at least in positive integers, and sorry, integration contour is this. The pure imaginary direction with slightly small positive number. And if I cross the integration contour in this way, in the positive side, then this integration is varied by summing over the pole at t positive integers, and that's just reproduce this expression. But that can be justified when exponential mu is small. But what we want to do now is exponential mu is large. Mu is positive and large, and that means exponential mu is large. And in that case, we should rather cross the contour on the left. And in that case, again, we can evaluate this integration by the residual sum over, we have the pole at the origin, and we also have the pole at somewhere like here. For example, in the ABGM case, and if you consider the leading part of the one small k expansion, the trace law to L is just integration of 1 over cos x half to L and 1 over cos p half to L. X and p are just classical number in the classical limit. And we can do that integration, and we get this. So these have the poles at negative, this numerator factor. So from the pole at the origin, actually what we get is the part of the large expansion, and from the pole at on the negative real axis, what we get is something which behave like exponential minus something mu, because this t is substituted by negative number, and that is not part of it. And this is one kind of the M2 instant. Another kind is the case where the three-dimensional volume contains the obifold zk obifold cycle, and in this case, the exponent have the extra 1 over k factor, so it behaves like this. And this is small k non-particle effect, so we cannot study by the small k expansion, but still by using Fermi-Gas formalism, we can calculate patch function, exact value of the patch function for finite k and finite n. Of course, m is also finite when n is not so large, like n equal 1 to 3, and so on. Then we can do the fitting and study this effect. This is correct. Yeah, this is k, not n. But if you are considering the M2 instant on left on the, I think related to your comment. So the first kind of M2 instant is sometimes called D2 instant, and the second one is sometimes called F1 instant. This is because if we interpret this obifold S1 cycle as an M series cycle, then this is F1 string, and this is D2. And if you consider this F1 instantons, then if you go back, we have 1 over k extra factor here in front of the square root. So in that case, the volume of M2-brane is the square root of n over k. non-square root of k. So they are not familiar with this effect in the middle. Sorry. And yeah, actually this final slide in the first section. So after Marmot found this experiment, for some reason many people, actually many people also study this non-bottom effect, very hard. Both the worksheet and both the D2 instance and both F1 instance. And they collected the lot of data, and as a result, they found actually this is paper they finally concluded, which is Marcos and three Japan people, that the non-pattern effects are related to the free energy logical string. And slightly after that, actually it's already commented in this paper, but it was proposed that this connection is not accidental for the efficient theory, but somehow universal for any Fermi system. So let me briefly review what it is. So let's suppose that the density matrix have the inverse, which looks like this. So some finite Laurent polynomial of exponential x and exponential p. And then I think it's already appeared in the Lacan-Son's talk that if we are given such finite Laurent polynomials, this encodes the some non-compact toric curve as reports by and this curve is called the Miller curve. And the claim of this Krascher's new paper, which is called logical string spectral cell correspondence, is that for such density matrix, we can consider the Fairphone determinant and then define the modified ground potential as I did for the efficient theory. And then this J have the part of the part, which is cubic polynomial. And then we have the non-part of the part. One of them is the F1 instanton, so exponential minus mu over k, and the other is exponential minus mu. And the claim is that these two different kinds of non-part of effect respectively given precisely by the free energy of refined logical string on Krabbe threefold in two different limits. One is the undefined limit, and the other is the Necros-Shatsui limit. And for example, in the case of efficient theory, the density matrix without rank deformation was this. So if we take the inverse, we just get cos x half and cos p half. And if you change the canonical position momentum operator by x plus p equal x prime, so x minus p equal x prime and x plus p equal p prime, then we get this four terms and u. And in this case, the Newton polygon is a collection of this AB. Looks like this, and this corresponds to the Krabbe threefold local P1 plus P1. And this T, there are two Euler parameters, and they are given. So for the case without rank deformation, we can easily get this equation. But even when M is non-zero, I don't explain at all, but we can still take the law inverse and calculate, and then as a result, we find it's still this Laurent polynomial, same Laurent polynomial, and the information of M just appear in the coefficient. And so and what I want to say, but the Euler parameter which appear in this formula, there are two Euler parameters. This depends on the mu is log of u and the capital N, like this. And also, sorry, I forget to put any papers, but of course, this is not only checked for the evidence theory, but also checked in many examples by, I think, in many cases by Marcos and his collaborator, and also Min-Shin Fan and his collaborators. Yeah, I also did it, but just one. Yeah, so this is the end of the first section. So let me move on to the finite properties. So yeah, actually, J is the J. This is the definition of J. Actually, J mu. This J is J mu. yeah, so yeah, let me first say the result. So it was found by these papers. Yeah, actually, this paper found something more fundamental than paper organized in this way. Anyway, they found that the finite grand canonical patch function of the ABGM theory, ABGM theory satisfy very beautifully the linear equation. And actually, this linear equation is known as the Q discrete version of the Van-de-Waals equation. This Q is this. And indeed, as I said in the previous slide, by using Fleming then we can calculate the exact value of the patch function when m is 0, and we can do the same calculation also when m is non-zero. And this is sample result for k equal 2 and n equal 0 and 2. And yeah, if you open the paper by Honda Okuyama, I think you can find the result until n equal 20 or something. And if you plug this to the grand patch function, you can check this equation is satisfied. Yeah, if I understand correctly, Marcos and Hatsuda and Albert Grassi, they found this equation, or actually more fundamental equation, that's experimentally by just by looking at these exact values. So sorry, that's right, but I didn't thought about it. Yeah, actually, some people try to say that this grand patch function itself has some physical meaning, but for me, this grand patch function is just a tool to calculate. So it's not the patch function themselves. Yeah, I think some people who try to reproduce airy function directly in gravity side try to claim that ECC patch function. For example, the airy function is given by this integration. So some people try to convince us that this mu integration appears as some integration over some massless mode. Yeah, but sorry, I'm not familiar with the approach. Yeah, so this Vanilla equation checks against the numerical data, but I think so far there are not proof. But only in one expressional case where k equal to infinity, and at the same time we also send m to minus I infinity with this m prime gift. Of course, this is just by only after the analytic continuation. But anyway, after analytic continuation, you can take this limit, and then actually the statement which says that the Abelian grand patch function is so the tau function of the K-Van-de-Waals equation leads to the statement that the grand patch function of the something called automatrix model studied by Zanochkov is the tau function of the usual Van-de-Waals differential equation. And this statement was proved explicitly by iteration of Widan. Yeah, this is really long time out. And this is a very rough idea why people, at least I believe, that the Vanilla equation is not the accidental for the eventuality, but maybe more universal for the various Fleming system. So yeah, the first equality is the TSS correspondence. We say that the grand potential is given by the Brusca spinning energy, but it means that the grand patch function is the summation over n of the Brusca spinning patch function. And in Pokemon form, this Brusca spinning energy comes the M2-brane in the M theory on the Carpius threefold, wrapping on the two cycles in Carpius threefold. And this setup can be also interpreted as the supersymmetric patch function of the 5D theory. 5D is living the 11 minus Carpius threefold directions. And then this equality is suggested. And on the other hand, in this equality, the mu is related to sigma, so the summation remains. And on the other hand, the 5D instant patch function, 5D patch function is evaluated by the localization, and that just results that the contribution is localized at the fixed point of the E1 symmetry, so given by instant and localized at the fixed point of the symmetry. So this is one way to evaluate the 5D partial function. And another way is, I think by this paper, is that we can blow up the origin by hand, and then the origin become P1, and then the fixed point of this isometry will become these 2 points. And in TS/ST is the topological string spectral theory correspondence, this one. Yeah, so there are two approaches to evaluate the 5D partial function. One gives the partial function is summation over the instant, and the other expression gives the partial function is the product of two summations over the instant. And yeah, it's argued in this paper that since originally the origin is just smooth, this blow-up doesn't change partial function, and then we obtain the non-trivial consistency relation for the 5D partial function. And actually, by using such this nonlinear non-trivial consistency relation, we can obtain the bilinear equation for the 5D partial function at the circular omega background. And yeah, I think this is the reason why we can believe that maybe there is a bilinear equation not only for epigen but also for more general density matrix. Yeah, the leftmost side is partial function, so the current partial function of the S3. So TSST correspondence, actually, I don't know how to understand TSS correspondence from 3D or, for example, it is 4 + 5 7, but this some 3D partial function is related to the topological string on certain Calabi-Yau threefold. That Calabi-Yau threefold depends on the density matrix of the Fermi gas in there. This way. And this topological string on this Calabi-Yau threefold and the 5D theory is related by identifying the Newton polygon with the dual diagram of Newton polygon. If it is the point, you can draw the dual diagram like this. And if you identify this line as the so-called P5-brane wave diagram, then that is 5D theory. Yeah, which appears here. Oh. So can I continue and maybe try to talk as much as possible in 2 minutes? Yeah, so for example, in ABGM case, this is the Newton polygon, the corresponding 5D theory is the SU2 with that matter. And actually, we can even read of the 5D parameters from this curve. And yeah, 5D parameter, one 5D parameter in this case, the Coulomb modular and the gauge couplings are given. The 5D partial function is given by this combinatorial formula by Nekrasov, and yeah, this instant partial function is given by summation by the Young diagrams. And yeah, what I'm quite sure is at least if we can use this formula, we can explicitly check that the tau defined by this satisfies the equivalent equation. Yeah, the difference between checking the binding equation for the grand partial function region theory numerically is that in this case, at each order in P, we can evaluate the partial function completely analytically for the other parameters as in other parameters. So yeah, at this on this 5D side, it's much easier to check and convince that the 3 equations satisfied. And once we translate this 5D parameter to the parameter of efficient theory in this way, this equation means the linear equation found by Gracious Marine and the Bobonic Gracious. And yeah, one thing I wanted to say is that so this is only the evidence example, but once we assume this road, we can search the linear equation for the more general circular Quiver-Transform theory by studying the Pavlov batch function of the corresponding system. We have similar formula, and then by using it, we can search linear equations. And maybe I should skip that part. Sorry. Yeah, actually, I did that exercise for slightly non-trivial setup where we have this. Anyway. So let me, can I talk a bit like 2 minutes? Oh, yeah, sure. Yeah. So then let me go to the recursion relation. So the idea is very simple. So now we have this equation. Let's assume this equation true. Then expand this in U and look at the coefficient for U to N. Then we have some equation which is written in patch function to N and the patch function to less sign. So let's solve it in patch function at rank N. Then we obtain the recursion relation. The problem is that the number of unknowns is larger than the number of equations by number 2. But this problem is solved by using the Hamilton duality. So yeah, in the previous section I explained the Hamilton duality, but I hope people know it. So when I talk about the Fermi-gas formalism for the ABJ theory, I assume that the relative rank M must be within the range from 0 to k. And what it means that the linear equation is supported only for m equal 1 to k minus 1, so that the shifted one, the m minus 1 or the m plus 1 doesn't exceed this one. But in the brane viewpoint, we can just consider m equal minus 1, which is this. And yeah, we can even do the Hamilton transition, and then we can finally find that this patch function is equivalent to the patch function with the relative rank within the range from the 0 to k. But the notable point is the smallest rank n changes in this way. And if I translate this relation to grad patch function, we obtain this. And so we originally have just these equations from m equal 1 to k minus 1, but let's naively set m equal 0 here and apply this relation. And then this equation is not supported from this previous argument of TSS T5 but by using the exact values, we find this is satisfied. So let's assume these are the actually satisfied equation, and then we have enough number of equations to do the recursion relation. And yeah, since I already talked 2 minutes, let me skip the new parts also. And this is the summary. Yeah, this picture is summary of this talk. So I introduced Fermi-gas formalism. Sorry, I wanted to consider the matrix model, and large class of them have the Fermi-gas formalism, and it gives the area function very easily. But on the other hand, I did this involved arguments that we have the relation between topological string and 5D, and then it starts linear equation. And if I combine this linear equation with the Hamilton duality, we obtain the recursion relation. And yeah, recursion relation, I didn't show any concrete example, but recursion relation, so just allow us to calculate patch function algebraically in, for example, from n equal to 0, which is patch function equal to 1, from 1, 1, 2, and so on. If you do it numerically, you can really go to very high n. So at least numerically, you can check the patch function in behavior by the area function. And I completely skipped, even in slide, I skipped. But for example, we can also study the non-pattern effect, which is still not clear for if we turn on the mass deformation in evidence theory, or the phase transition, which occurs if we increase mass to some finite values. But anyway, we are still not satisfied because what we can get by using recursion relation is at least at the level of one part of the expansion. That's what we already know from the class. So what I should do next is to try to find the linear equation for non-Fermi-gas stuff, and yeah, I wrote some ideas, but yeah, let me stop here. Thank you for your attention.
over time.
Can you write it only for one?
Well, what I did is actually in ABGM case, recursion relation is not recursion relation. It's degenerate and you cannot do recursion. What I found is this. So I introduced 2 mass parameter. I don't know how to do it with 3 mass parameter. This is one, and another one is when we set k equals 1, m equals 0, ABGM is 0 to this model with L equal 1, sometimes called the ABGM theory. And of course, in that case, we have the recursion relation, but in this paper in preparation with the student in Fudan, I found the same similar recursion relation also exists if we increase the number of flavors. Yeah, I think I can just show the question. Yeah, this is the recursion relation for the massive division theory. The problem is that if you take m1 equal to m2 equals 0, this factor becomes sometimes 1 over 0.
Okay, but make it fast.
Can you show this bilinear equation once again?
For ABGM, this
Is it really bilinear or is it just some quadratic?
in terms of the Guzzi, in terms of Guzzi or in terms of patch function, it's bilinear. So everything is quadratic. This is Guzzi square. If we expand it to z square, z square.
And what's the origin of this equation again? Is it proven?
So sorry, what?
Why does this equation hold?
Yeah, this is the argument, and yeah, what I said here is I attribute this bilinear equation as the as a blow up Nakajima Yoshioka blow up equation, and that equation is actually not bilinear. Sorry, I'm writing in very abstract way.
Well, anyways, just, I mean, in short, is it something that is proven or is it a conjecture?
I think in simplest case, Kubernetes list case proves, but I mean, the technical proof was given by this Bernstein-Sheshkin in this place.
Okay, so let's end here. Let's thank the speaker again.
Thank you.